So we're going to get to this. We are going to bounce off of this gist, which is a sort of summary of every optic that we know of so far in a really condensed form, and draw some analogies with the isomorphic reasoning stuff that we were doing in the 6-hour talk on Wednesday, which is kind of cool because most people don't think, hey, lenses, counting, you know? But actually, it turns out to have this really interesting relationship that that's going to be mind-blowing to some degree. Like, it'll totally make lenses click for you, I promise. So we just have a short gist here with, you know, all of our favorite friends, all of our favorite optics. And we're going to go through this one by one and really, like, tear into this stuff and understand it. But first, we are going to have to talk about, let's see. Don't look at that. It's in my Haskell directory. First, we're going to talk about where we were leaving off in the isomorphic reasoning thing, where we were talking about adjunctions. Right? We had this sort of nice. Okay, we had this nice equation that we were talking about. Like, how do you prove generalized distributivity theorems like A times B plus C is equal to A times B plus A times C from a categorical standpoint, right? So we saw it in types. That kind of makes sense. We understood coproducts like either to be addition, and we understood products like tuples to be multiplication. And we saw how they respected the laws of arithmetic when you view types from a certain vantage point. In this case, isomorphism classes of finite sets, sets, but numbers in terms of isomorphism classes of finite sets, where addition and products were actually respected in the sense that they conform to the laws of arithmetic, and you could just treat types almost like arithmetic modulo some edge cases, like 1 to the 0 and 0 to the 1, or 0 to the 0, sorry. 0 to the 0 being 1 in this case. Okay. Right. So we ended with a sort of whirlwind through understanding currying and pairing, so the universal properties of products. Currying being the morphism from A cross B to C was isomorphic to a morphism A to B to C. And pairing, which stated that A plus B to C was equivalent to saying A to C times B to C. And we saw that just by looking at the diagram for coproducts and products and sussing out some information, you know, noticing that we had a pair of functions which characterized a coproduct, and a pair of projectors which characterized products, right? Is everyone comfortable with that? Good? Okay. Now, here's a sneak peek of kind of where we're going to go with this, right? This is going to be our main theorem for understanding adjunctions, and especially the universal properties that we understand in Haskell pretty much every day, as just applications of this theorem, which we'll get to, which says, if I have a small category, or a locally small category C, so home sets are sets instead of just collections, then if I have a category J, which indexes my category C by some diagrams, which we'll explain, then C admits every limit and co-limit in the case where you can form this adjunction with respect to a diagonal functor, where you have co-limits being left adjoint to a diagonal functor, and diagonal functors being left adjoint to limits. And they all form functors in and of themselves. Right? This is everything that we just did in the previous talk. Right. And we have the famous quote, which you can't talk about adjunctions unless you talk about this quote. Adjunctions are everywhere. They're a huge point. They categorize dual theories for everything in category theory. So if you think about proving a statement for some category or some functor, you have automatically proved its dual statement. And it's dual statement if there is an isomorphism between those dual statements, then you have an adjunction, right? Right, and they are extremely relevant to functional programming in the sense that every adjunction gives us a monad and comonad pair. And we can actually just look at these monads and comonads and we can recognize them to be very familiar functors that we deal with every day, like lists. Right? So let's start with some definitions here. If anyone's unfamiliar with this notation, just holler and we'll discuss it further. But we call an adjunction this right here. So we let L be a functor from some category, some locally small categories in this case. We call L a functor from C to D, R a functor from D to C, so going opposite ways. And they are adjoint, or there is an adjunction if there is an isomorphism between Hom sets where L takes a parameter and has some target, and that same parameter, and that's isomorphic to a Hom set from that same parameter to R applied to the second parameter in the domain category for L, right? So this just means equals are equals to the other equals, and dashes are equals to the other dashes in this case. So it's the same component. Any questions so far? Yes?
You lost me on the notation with the, I understand the dash, double dash, but not with the R and L embedded in.
Right, right. So think about L applied to dash. So if you imagine for all x, L of x. So this is just like a placeholder for applying L to dash, whatever dash is. And same with equals. R is applied to equals. So if you look down at the component morphism here, which I explained, so the components of these morphisms are you fill in the x and y, and they will have this relationship, right? So effectively, adjunctions are natural isomorphisms in set between morphisms or sets of the form Lx to y, which is isomorphic to sets of the form x to rx. Or sorry, ry, sorry. Yeah?
Does it mean for an isomorphism to be natural? Like this is an isomorphism within the category?
Yes, this is a bijection of sets.
Yeah,
Yeah.
So what makes it natural?
It's natural in the sense that this is a component of the natural isomorphism where I erase x and y.
Oh, so phi is natural.
Yes, yeah. Phi is a natural transformation. Phi sub x comma y is the component of the natural isomorphism.
Going from x and y to the isomorphism, that's natural.
Yeah, yeah. So you fill in the x and y. Right? Comfortable? Right? So effectively here we just have whenever I can construct this natural isomorphism and these two functors with this relationship, then I have a bijection of sets for every component, every pair of inputs to that natural isomorphism, right? So for all x, y, L of x to y is isomorphic to x to R of y, right? And you can just imagine we're in set for now and forget about D and C and just like fill it in with Haskell types, right? They're both on the outside. So left is on the left and right is on the right. They call them left and right for that reason, actually.
I always get tripped up when there's like three of those.
Yeah. When there's three, you just break them up and sort of associate. And then you have like diagonal on the left and limits on the right, or you have co-limits on the left and diagonal on the right. Right? And the position of the functors remains the same for every adjunction. So just depending on what side of the sort of turnstile they're on, that's what you're going to get. Right? Ooh, somehow I clicked it. Weird. Okay. So we have some universal properties, which are sort of equivalent to the definition that we had before. These are called the unit and the co-unit of the adjunction. So an equivalent statement to what we just said is to say that for two functors that are adjoint, and if there exist natural transformations from the identity functor on C to the composition of right and left functors, and a natural isomorphism from the composition of left with right to the identity functor on D, then if they satisfy this triangle identity, which we're not going to go into too hardcore, then they are an adjunction. Okay, so if you imagine, forget about the triangle identity for now and just stare at eta and epsilon for now. What do those remind you of? Yes, that is pure and copure. And actually, we're going to find out that R compose L is a monad. And this is actually just return in our monad. And likewise, L compose R is actually just extract. Or L compose R is a comonad for which epsilon is extract. So you can replace that in your head, where M is really just the composition of a right with a left adjunct. Okay, so we're actually going to see an example of this because it's actually a lot easier to work through these examples than to just stare at equations all day. So here's a good one, and actually the punchline to this is really interesting. Consider a forgetful functor from D to C, or replace C with set. Okay. Let C be in C. A free D object is an object in C with respect to the forgetful functor, satisfying a property that a left adjoint might have if it existed and were left adjoint to a forgetful functor, and satisfied this diagram. That's a free construction right there. Things that look like a left adjoint are free functors, as long as they're left adjoint to a forgetful functor. Yeah?
Where did the uniqueness come from?
Right, so this is just a construction. So the uniqueness property is that if I have any morphism from C to my forgotten object U of D, and any other morphism to any other U of D prime, then for any morphism between D and D prime, then this induces a unique morphism H, or H, yeah. So if I have any H from D to D prime, then this induces a unique morphism, which is the image of the forgetful functor on H.
Is there a way to see uniqueness from the definition of the adjunction? How did the diagram tell them that?
Right. We'll go through an explicit construction in just a sec. That's a good question. Right. So this is just the high level what a free object is. Something which satisfies that if I have C and I have two morphisms to any objects in C that are the images of a forgetful functor from D to C, then if there's a relationship between D and D prime, then I have a relationship between their objects with forgotten structure in C. Okay? So a classic example is the free monoid construction on sets. So consider S to be an underlying alphabet, so just a set with some elements in it. And let MS be the free object in Mon generated by this set. Okay, so we're just going to call it MS. Any set function from S to an underlying set of any other monoid, say UN, extends uniquely through this object. So I can construct this diagram here where I forgot my. I can construct this where I have S to this. Let's see. This guy right here. And if I have a morphism to any other underlying set, choose it, to be the forgetful functor from some other monoid to sets. So if I have, some U n here for some monoid n, which is the underlying set of n, then if this guy exists and this guy exists, then I know that because this monoid is free whenever I have an h from ms to my other monoid, then this is going to extend uniquely to a set function, which is just the restriction of generators into the underlying set of un. So this is actually UH in this case. Do you see the relationship that's going on here? MS is our free object, and the forgotten functor, or sorry, the forgetful functor here is an important part of this. Like, it tells us exactly what our generators are for this monoid. So you end up with this adjunction here. In monoids, the free functor to any other monoid is isomorphic to saying, if I take my underlying alphabet of my free monoid, then I have a morphism to the underlying set of that n.
So is this the same as saying that the subcategories of just restricting monoids to ns and the same range under the functor, those are adjoint?
Mm-hmm. Yes. Yes. So I have this guy right here. Right? So this is kind of, this is familiar to us in a totally different way, right, than we're used to. Because if we look really closely at this over here, then we have something very familiar. If this is a set of letters, and this is the forgetful functor, so the right adjoint composed with the left adjoint on S, then what do we generate in a free monoid when we forget all of its structure? It's the combination of all words in S, which are combinations of letters in S. So we end up with something that looks like, you know, A, you know, infinite AB, blah, if S is equal to, say, A, B, C, right? So we end up with this giant collection of combinations of words built from the set S. And this is exactly a characterization of a list. Lists are free monoids in the sense that their image under a forgetful functor is a combination of all words with respect to the underlying set. So any combination of possible A's, for instance, if this was a Haskell type A, then this would be a list of A, because it contains all possible A's and combinations of A's. Right? So this top function here, f, is really just pure. On board? Harris? Ah, I thought you were raising your hand. Okay. Every single free construction takes this form. You choose your C in your target category, like set. You find an object that looks like a left adjoint. And then you show that the image under a forgetful functor, in this case, or sorry, yeah, the image of a forgetful functor, and any other function over here has a unique morphism that completes the diagram whenever these two have a relationship. Right. Cool.
Can you just extend your example just a little further? In the list case, what's an example of the G and U of H?
Right, okay. So F is classically called star. This is the clean construction on a set of generators. So this is what we call the function, this guy right here, star, which consists of, we take the empty word to be like the empty set, where it has a few rules. Concatenation with any A is equal to A, right? So we're just like concatenating elements. And then we say A star B is equal to AB, and we just build via successive iteration on our set words that follow these rules, and some associativity rules. So like B C is equal to. So you're kind of building a monoid without stating that it's a monoid. And then it acts like a monoid when you start looking at it with respect to any other monoid that you know of. Right, so that's one example.
Star from regular expressions.
Exactly. That's referred to as the, clean star construction.
That's F in this diagram?
Yes, exactly. Right, so we could just erase this guy and just say star. Right? So, for instance, free groups follow this, except in addition to this, you have the additional set of rules which allow you to insert or collapse words. So which says that I can always sort of move up from A to A inverse in the sense that if I have any word W and any word W prime, then I can always map this to W A inverse W prime and insert sort of trivial statements into my word. Or down moves in the sense that if I have any A and A inverse, then if I have A inverse W prime, then this can just map to W and W prime, right? In the sense that I can collapse any inverse to the trivial word, right? So this whole collection defines a free group. And this is equivalent to the Klein star, except with these two additional moves, right? And then the free product is just the concatenation of words with respect to these rules, right? Yeah. So let's move on to some, actually, I'm going to cancel this real quick and I'm going to go to main. And I'm going to show you some of the constructions that we went through. Shoot. Yes, we're already here. Okay. Right. So, right. This guy. Okay, so we actually construct one in the sense that we, if we take a look at pairing, for example, the set of functions from a coproduct to any x is isomorphic to the product of functions from b to x and c to x, in this case. Right? How do we get there? What I was talking about yesterday was that the trick is to notice when you have an adjunction. So if I have the set of morphisms from b plus c to x, and I know that this is isomorphic just operationally. For instance, say I'm trying to construct an adjunction, and I just know operationally that this works. Then if I look at this guy, I can notice something about this form, right? I've got two functors here hiding. What are the functors? You know these. Everyone knows these in here. Yes. I have the product functor, for one. The guy that goes, that guy's a functor, right? Along one of the components. And I also have that guy. That's either. That's the functor on the right, right? Left bias or right biased either. So I can take a look at this and I can sort of erase the relevant parameters and I can form an adjunction just by going like that and like that. And I can take a look at that and I can look at this and I can say, what are the functors here? There's another one. There's let's say, no, because if I look at this, what is the product? What elements am I going to have in here? Right, I have the product of functions from b to c and then the product of functions from c to x. Right, so I have functions that look like f cross g, where f goes from b to x and g goes from c to x. And then I can notice that this is equivalent to saying b cross c to, x cross x, right? And notice this here. This guy's on the right. That's a functor. That's called the diagonal functor. Yeah. So what I end up with is a statement which is equivalent in this case, which is that the coproduct is left adjoint to the composition of two functors here, right? So I have whatever dash c to delta whatever. And actually, if I fill in, I should use b in this case. If I fill in the positions that I just erased here, so I have this guy, and I forget about that guy, then I have something that looks exactly like an adjunction. And in this case, I have the statement that the coproduct functor biased on the right is isomorphic to a composition of functors, which is the product functor and the diagonal functor, right here. Cool? This is exactly the form of an adjunction if I fill in c and x. So if you imagine, I just erase this, c, I have x, c, and x. And I have an equivalent statement in the sense that this is actually just isomorphic to saying b to x cross c to x. That's pairing. So we've seen that coproducts are left adjoint to a diagonal functor, right? And I know that these limits are here in the sense that, don't worry about it, in the sense that I will always have this form whenever I try and take functions from a coproduct to x. Okay? So that one's a little complicated. The one for products is a little bit easier. Everyone knows this one. What's it called? What's the universal property of products? What does that give you? It's currying. Everyone knows currying. In which case we have A cross B. Actually, I should get ahead of myself. B to X is isomorphic to A. Actually, I'll do B because that's a little nicer. C, A to X. What are my functors? Can anyone spot a few? Yeah. One already featured. Yeah, there's product on the left, right? So we have A cross whatever. That's one functor. What is our one on the right? Yeah, it's just reader, right? Or co-reader in this case. Actually, no, it is. That's right. Yeah. So it's just reader. So products are left adjoint to readers. Because if we fill in any, or if we erase this, and we erase this, then I have this. Or, sorry, this is A. And that's a natural isomorphism. So currying and pairing are really just natural isomorphisms, and they define an adjunction between two functors. Cool. It's been half an hour, so I'm going to kind of speed through a little bit. Let's go back to our optional stuff. Right. So there is a slight generalization of this idea in terms of something called diagrams. In fact, there is a category of diagrams, which are functors from some category to a target category. And this functor category defines shapes, which are directed graphs, where the edges and the vertices haven't been labeled yet. It turns out that limits and products, as a special case, are cone-shaped diagrams like this. Right? These are called universal cones. And whenever I have a cone-shaped diagram from J to C, then if I have an object n, or a special object L, such that for any other n, those n and 2 functions from n to any other x and y in the image of J, then those factor uniquely through the projectors in L, right? That's the general case that we call a limit. And you notice this, it looks exactly like the product functor, except we've, yeah?
Well, I was going to say, except for that one on the bottom.
Right.
Which was that?
Right, that's just a morphism from x to y in this case. It's just the image of any relationship between x and y under J. Right? Forget about it. Well, it's still there. It's harder to assess. That's all. Right? And you have the exact same thing for coproducts going the opposite way. Right? And that's a colimit. So basically, the only abstraction really between products and coproducts is the fact that we note that in the general case of limits and colimits, that we're coming from a diagram category. And that's it. Right? Just reverse the arrows. And you've got a colimit. Now, I claim without proof that this is a functor, that these two constructions are functors. And actually, we can sort of operationally understand them to be functors because we've all constructed the product functor and the coproduct functor, which is just either, you know. And we know what that looks like. More generally, by picking the functors, or actually just by looking at universal properties like currying or exponentiation or pairing, we can look at the functors involved, and we can reverse engineer an adjunction just applying the same process over and over and over again. And we note some interesting things, like the product functor being left adjoint to the exponentiation functor here, who's actually, and this is an exercise if you want to do it, the co-unit of which is $. If you take a look at the composition of these functors, you just end up with the evaluation morphism, which is kind of interesting. And we have the, sort of standard statements that we're used to here. And this helps define our arithmetic. These are all the laws of our arithmetic that just come popping out of these adjunctions. As soon as you have a universal property like this, you have the basic laws of arithmetic. Right. Now, the proof of this, the proof of the previous one, is actually relatively simple now. It's a one-liner. That's simple in heavy quotations. You realize that if you're trying to prove, say, AX cross B plus C, the distributive property, right? Let's do this one. Without getting into the adjunctions, how would you prove A cross B plus C is isomorphic to that, right? Step by step, how would we do this? Where can we go from here? We also have to consider Yoneda in this case, right? I'll start it off, okay? We can note that the Hom, or that this is isomorphic to the Hom of this, right? That's Yoneda. That's the statement of generalized points, okay? Now where can we go from here? Just think general arithmetic. How would you do this? Yeah, curry. Right, this is isomorphic to the Hom of right, B plus C and the Hom of A to X, modulo a swap, because I know how it's going to turn out, and that's nicer. Right, and where can we go from here? Right, we have one law that we haven't used yet. Pairing. Right? The Hom from a coproduct to anything is the product of Homs. So we can go further to the left here. The Hom of B to Hom of AX cross Hom of C to Hom of AX. Right? Now where can we go from here? Yeah, we can curry. We can just do Hom of C of A cross B to X again, right? And Hom of C to A cross C to X. And we have one last step. And we know this form, the product of Homs, because we've already gone to this, but we can come back from it now because it's an isomorphism. Right? This is reverse pairing. This is unpairing. So we can just go isomorphic to Hom C of A cross B plus A cross C to X. And this is isomorphic under Yoneda to just A cross B plus A cross C. And there's the proof. Cool? All right. So that's adjunctions. Right? It's complicated. It takes some practice. Definitely learning how to spot a functor in category theory is very different from how to spot a functor in Haskell. But it is a language, and it's just a language that we haven't spoken very often in the community. But it is important to notice when you have a functor, right? So like either takes a totally different character, but we're all familiar with either in here, right? The functor is like a one-liner, but that was tough. And same with the product and the exponent, the reader and the co-reader functors. They're all functors, but we just need to learn to recognize it. But all these arithmetic properties drop out. So you get this all for free. And you can use this in your isomorphic reasoning whenever you're thinking about types and simply refactor as needed. Right? And it follows that if these are all sets, then as we discussed in the isomorphic reasoning class, then their image under the cardinality functor, if we take their isomorphism classes of the number of elements in those sets, then that gives us natural number arithmetic. Right. Now, here's where we can get into profunctors, and we've got 10 to 15 left, and I would love to go to 15 minutes, if that's possible. If you notice the shape of adjunctions, you actually notice something interesting. That you have, if you forget about x and y at the same time, like you erase the parameters and you just deal with dashes, then you end up with one parameter, the x, the one on the left in the Hom, as being in a contravariant position, and the one on the right as being a covariant position. And their target category is sets. So really, Homs and adjunctions, less in general, Homs are contravariant and covariant at the same time. Contravariant in the first parameter and covariant in the second. And they go to set. So the statement of adjunctions, we call that a profunctor. The statement of adjunctions is actually, I have an isomorphism, a natural isomorphism of profunctors. And that's the starting point for optics. Crazy, right? Right? And we call those heteromorphisms, for everyone that's wondering. It's just useless, but optics, right. Okay, so we can all relax now. we're probably not going to get to any of the hard theory in profunctor optics at this point, but where we can go is an interesting arithmetic route with respect to optics. So imagine I have a profunctor, right, P of AB, and imagine I had a monoidal action which took a profunctor and did something with it monoidally. So I had like a tensor of some kind acting on my A and B in the profunctor. So P of AB to, P of A cross B, or P of B cross C. Right, so just take a look at, for instance, choice, where my monoidal action is coproductive. I just add a parameter on the right. Right? This is what's called a choice profunctor in Haskell, right? Where a profunctor is just something with a dimap. And suppose I were to change that tensor to, or that monoidal action to a product of different kinds. So exponentiation is a monoidal product. Products are monoidal products. Monoidal actions. Coproduction is a monoidal action. And I'm not going to prove that, but just take it at face value at this point. And suppose that I can do this on lists and such, right? Well, it turns out that I can compose these actions, right? And if I look at the general form of an optic, my claim is that this is an optic. It's just a dimap. And if I look at any of my optics, then the choice in optic is actually one-to-one with a choice in tensor. So depending on whether it's plus or multiplication or exponentiation, I have a new optic, or some combination of those tensors.
What were the bottom ones? Glass window.
Oh, yeah, so I invented window. I'm sorry. It's a little bit crazy, but you can just take these to their logical extreme and just form valid optics by combining these tensors in coherent ways. Right? And that's all these are. Like glass is a combination of tensors, and windowed is a combination of all the previous three. And I will show that these actually form valid optics.
So combination, is that actually composition?
Composition, yes. Yeah. Right. So that's all of profunctor optics, modulo some details. But the really interesting thing is about to come next, right? Because this really makes it for me. We have analogies to arithmetic properties in the form of optics, right? Optics are fundamental arithmetic properties. Optics come naturally in any language. This isn't just a library that appeared out of nowhere. They are fundamental abstractions that we can apply to products or sums. In the case of, for instance, ISO, we show that two things are equivalent, right? In the case of prisms, we show that we have a less than or equal relationship between the thing on the left and the thing on the right. In lenses, we have a divisibility relationship. And if you think about it, this really makes sense. If I have a record and I'm trying to pick out or see if I have a witness to a lens into that record, then really what I'm showing is that that element divides my record into one unique portion, right? And through some sort of tedium, we figured out that greats, which were the exponentiation optic, corresponds with logarithms, where you give the base, and that base actually produces the A and the B, right? And glass being something which packages up that base with it. And window acting like exponentiation, right? So we have some examples. Consider the piano naturals. We're just incrementing or successing on unit here, right? We have 1, 2, 3, 4. And I provide some nice syntax so we can just flip here. It's just, it makes things nicer. All right? So if I want to divide anything by the first component with respect to any A, then I'm going to call this first, which you'll know is like a sort of fundamental of strong, right? You create the product on the left. whereas in second, you create the product on the right. And I can do the same thing with prisms. And you'll notice by analogy that this kind of actually works. A is less than or equal to A plus B for natural numbers. Right? And same as B divides B, or B divides A times B, and A divides A times B. Right? And in fact, here's the log analogy right here. A log based, which is our glassed optic, an exponential, which is slightly crazier with respect to windowed. But we're not going to focus on that. Let's just focus on, how about this? 2 is less than or equal to 3, or less than or equal to 2 plus 1? Yes, we have a witness in the form of left. 2 is less than or equal to both, at least one of the thing on the left or the thing on the right. So this tells me that I have at least one case. Right? 1 is less than or equal to 2 plus 1. As long as 1's on the right, I can provide the evidence that right is a witness to that relationship. Cool, right? And in the same way, I can show that 2 does indeed divide by 3, or divide 2 by 3. 2 does divide 6. I have a witness right here. It's underscore 1. It's first. Because it divides the first element. And likewise, 3 divides 2 times 3 on the right. Crazy, right? And that's all the time we really have, with the exception of questions. But I want you to think about this and be left with, what are optics? They are fundamental relations. And if you think about profunctor optics as proof-relevant relations, then the optics that we consider for records and sums and various data structures like that, though the optics correspond with fundamental arithmetic relationships with respect to the type arithmetic that we established in isomorphic reasoning. Oh man, I don't know if I can do that. This is all improv at this point. Yes, so with respect to sums and product types, the optics correspond with fundamental arithmetic relations between the choice of optic and whether it's a sum or a product. Yeah, something like that. I don't know. I don't know if that was isomorphic. I hope it was. Okay, yes?
Easy question. Dot ampersand connected to traversing. How do you read that? Is that much?
Oh, it's bullshit notation.
when you're saying it to yourself, what do you say?
That was, I couldn't think of anything better.
Is it
But
multiplication or?
it's, okay, so here's a cool thing about traversals. They correspond with Taylor series of a type. So my traversal, if you think about what an applicative functor does or a traversable functor does, it builds up structure for each A and deposits it in a monoidal functor, which is an applicative. And in fact, you have an analogy there where you have, is A a component of the product of lists, as we saw in the free monoid? These are just like words in A times some constant. And you can build Taylor series from this.
So it's a sort of power series?
Yeah, exactly. Starting at the unit for the monoidal action.
Is it picking out a term of power series?
Yes.
That's a common thing you do in combinatorial.
Yes. This is touching on species a little bit.
Yeah, okay.
We're getting there. Right? But it's coming from a categorical viewpoint. Right? And actually, we can show that every optic, and this is going a little longer, but this is sort of, take this at face value, don't read into it too much. Phi over there is a monoid, or sorry, a monad, which generates every optic and is left adjoint to theta. And this is the work that I've been working on with some folks with the Applied Category Research Group, Bartosz Malewski, and a few other folks. And we can show that we have these kind of analytic functors which describe our traversals, which is kind of cool. It's just, yeah, we have some fun stuff. So our Taylor series actually looks like we're an expanding analytic functor, and we have this valid Taylor series here.
Is that for unlabeled? Just going with the common thing. So in species you have the different kinds of power series.
Mm-hmm.
Is this one that presents one for unlabeled structures, one for labeled?
Yeah, this would be
One
unlabeled.
corresponds to exponential gener- The latter corresponds to exponential generated functions.
Yeah, this
Which one is this?
this is labeled.
Labeled.
Yeah. Right, you're labeled by type.
Okay.
Right. Yeah. Yes. So my ending statement is please learn optics. It's very cool.
Is this on the same level as the relationship between zippers and differentiation?
Very similar, actually, but not quite. I actually never read Connor McBride's paper, but I will talk with Tony and see if we can establish some more to this. I know that greats correspond with zippers, but I'm not, I haven't drawn the connection yet. I do want to get to derivatives and integrals if I can. But I think we can rebuild calculus with all this type arithmetic stuff. Yep, okay, that was it.